So I'm Tommy Wong, and I'll be presenting on applications of using UNet in semantic segmentation, particularly in the characterization of radiation-induced defects in images from transmission electron microscopy. So semantic segmentation refers to assigning class labels to individual pixels in an image, or say in a frame of a video. So here are some examples. This is a street view, which when semantic segmentation is performed on it, it can identify pixels belonging to pedestrians or cars or the road or the trees. And something that's um, more more relevant to defect characterization would be in this example of an augmented reality microscope. It's a light microscope examining tumor cells, and it could identify tumor cells in real time, particularly their locations and each pixel that is part of a tumor cell. So the basis of all fully convolutional neural networks, which is what is used for semantic segmentation, and particularly the UNet architecture, consists of convolutional layers and then followed by max pooling layers. So the convolutional layers contain all the neurons, and each filter has a specific number of neurons, and when it slides through an image or an input, then a convolution is performed on that region, and by multiplying the weight of each neuron with the pixel at that location, and then taking the sum of it, it yields the output. There is a modification to normal convolutions, which is dilated convolutions, and with dilated convolutions, the convolution kernel is expanded so that there are gaps between each neuron, and by performing dilated convolutions, a wider view of an image could be obtained while making fewer number of steps, basically. So there's a trade-off between the field of view and how detailed you want each layer to examine the image. And so after performing convolutions, max pooling is performed to further extract the salient details or the features of each image. So max pooling simply refers to taking the maximum number or maximum value out of as that max pooling kernel or filter is being slid through the image. So that downsamples an image from for a 2x2 filter, it downsamples an image from 224 by 224 to 112 by 112, so it halves the size. So the UNet is the state of the art for semantic segmentation. There are improvements to the UNet that will be covered in the next slide, but essentially the UNet is able to it uses an encoder decoder structure to assign labels to each pixel of an image. So the encoder has a structure that decreases the size of the input progressively, and there are more layers as the encoder approaches the middle of the network to extract more features, and then it's expanded back to the original size using upsampling, so that there could be a 1.1-to-1 correspondence between the output and the input in terms of the size of the image. Another important feature of UNet structures is are these skip connections. So these skip connections bypass the encoder or bypass the deeper layers of the encoder block into the decoder block. And so these skip connections preserve the big picture of the input data. And so here is an example of which using UNets, the atomic locations on this high resolution STEM image could be identified, and and it's also identified by the class of the atom. So it shows a silicon carbon defect structure in the middle. So there are improvements to the UNet. The current improvements to UNet is UNet 3+. It incorporates additional skip connections called full-scale skip connections. So these skip connections take in both feature maps from the encoder. So data could bypass deep layers of encoders to the decoder, but it also allows skip connections from within the decoders itself. So it could incorporate data of various scales from the finest of scales in the middle of the UNet to big picture information in both the encoder and decoder. As well, the UNet 3+ incorporates full-scale deep supervision learning. So what it means is that in the decoder side, each decoder block has a side output. So it outputs a mask, a label mask or classification mask of the input, and to calculate the loss of the training, it becomes a sum of the losses of each individual stage, either through the calculation of binary cross entropy or categorical cross entropy or focal loss, and taking that sum across all the decoder stages that yields the total loss for the entire network. And so these improvements purported by the authors allow some improvements in the accuracy, but it obviously also increases the complexity of the network. And so to train a UNet, you would have an input of the original image, and that's mapped to an output of a mask of that image. So typically 0, which is black, is reserved for the background, and positive values would be reserved for features of interest. So for example, in this image of TM bubbles, the bubbles would be labeled in white or 1. And if said image is an image of this location, loops of different kinds, and these loops could have different integer values for different types of dislocation loops in different habit planes. So the loss function of the UNet typically is a cross entropy function, either binary cross entropy for only 2 classes or categorical cross entropy functions for multiple classes. At times, focal loss is also used which is a modification of cross entropy functions by introducing an additional factor to address class imbalance. For example, in bubble images, it might be useful because there is a higher background compared to class 0 compared to the bubbles, which are class 1. Dice loss could also be used. It's basically a loss based on the IOU, or the intersection over union between the prediction and the ground truth. So that's also very applicable, especially for image applications. For the optimizer functions to perform back propagation, typically atom optimizer is used these days, but also stochastic gradient descent has shown some improvements over atom, even though it's an older algorithm when it comes to data with high class imbalance or sparse data sets. So compared comparing UNets to other available segmentation networks, including Mascar CNN and YOLO version 7, which also includes instance segmentation functions. So this is really a comparison between semantic segmentation and instance segmentation, which for instance segmentation, only parts of an image is being segmented to identify to give a class label to each individual pixel. So the pros of using UNets over the instance segmentation networks is that it's typically a simpler or shallower structure. It has fewer layers compared to, for example, YOLO or Mascar CNN, which could go up to more than 100 layers. For UNets, there are many UNets only have fewer than, say, 50 layers, and it is able to perform similarly. It also, because of the simplest network structure, it could also require less training data because it has fewer parameters within that network to be trained. And UNets could also handle larger images, and particularly UNets could actually handle images of different size much more effectively than Mascar CNN and YOLO version 7, because Mascar CNNs and YOLO version 7s, they incorporate a branch on assigning classification labels to entire bounding boxes, and that requires a flatten operation. And because of that flatten operation, it simply cannot process images of different size. That creates a bottleneck. But with UNet, because of its fully convolutional structure, it's able to process images of different sizes, since it's just sliding the convolutional kernel over an image. And in their cases shown where the UNet is able to better discern overlapping classes, again, this could be due to the fact that Mascar CNN and YOLO networks require bounding boxes and give bounding boxes as an output, and that's hindered by overlapping classes or overlapping labels. The cons of UNet is that it's typically slower when it comes to identification. So it's not used as much for video classification or real-time classification compared to YOLO networks in particularly. And depending on the applications, it could also be less accurate, but that's also highly dependent on the images and the application of the network. So the UNet could be used as part of a machine learning training and classification workflow for identifying defect structures by generating the class labels. And after labels are generated, more traditional computer vision tools could then be used to actually measure the size of these generated labels, since the network doesn't actually give measurements or other physical data. So here is an example of detecting helium bubbles using UNet. So I'm going to quit the presentation and go to the code. Strata, am I still sharing the screen? Are you seeing
Yeah, you are.
Notebook? Okay, so this is a notebook for training the network. And so typically it begins by selecting some training images and preparing the data for training, such as these few images shown here. And then there's also a validation set to ensure that the network is being trained properly so that the loss is continually decreasing. And then because of the small amount of data that typical TM experiments have, image augmentation or data augmentation is typically used to increase the amount of data. And for example, the images could be resized or zoomed, or adding noise to it to increase to prevent the overfitting of the network. And also particularly because these images are very large, so they're actually cropped into smaller images for training. And so this is
show me your results, final results, what you got.
And so after training, this is an example of the prediction. And so with this unseen image, then these labels are predicted using the UNet network. And also using some post-processing, then you could actually highlight these labels and get the radii of these bubbles and yield a distribution of these bubbles.
And this is you're doing by using OpenCV, right?
Yes. So this is actually done with scikit-learn.
Okay. So I have a question. So are we okay? Just give me heads up when you're done with the presentation.
Okay, I'll run through it then. Okay. So here's like a result from similar to what was shown before. And it gives an IOU of between 0.8 and 0.9 depending on the image. And this is just showing how dilated convolutional layers could actually preserve big picture information better. So if you increase the noise level of the images used in training, the blue curves are networks with dilated convolutional layers. The red curves are using normal convolutions. The IOU shows an actual a kind of a significant increase between the networks that use dilated convolution layers, especially at very high noise levels. So because the noise actually, while it affects while for small regions, when noise is applied to the image, it renders it incomprehensible for both the network and frankly for human eye. But if more big picture information is preserved, so that the network could examine the entire image better, then it enhances the accuracy, or rather it lowers the drop in accuracy because of noise in the data. And so UNet is a class of encoder and decoder structure, and autoencoders has a similar structure, and it could be used to extract underlying physical information in the middle between the encoder and the decoder. For example, by looking at these images of various steels, the actual concentration of different elements could be extracted using autoencoders and variational autoencoders. So in summary, the UNet is widely used in semantic segmentation, and that defect microstructures of different types could be identified on a per pixel basis. The UNet could also be incorporated into machine learning workflows to specifically to identify these labels, and after which then these labels could be identified using a host of computer vision tools to measure the size and gain other physical information out of it. And similar networks which use the encoder decoder structure could be used to extract physical information directly from images from TM experiments. So this is the end of my presentation.
And now it's the time for Discord, right? I have several questions. So first of all, in the beginning of the slides, you told that when you were explaining the architecture, you mentioned that we are using neurons in those convolution layer, like in the very beginning, yes. So I want to see where are the neurons here. And my question to you is, it doesn't, this network doesn't involve, you have two kinds of layer, right? One is the convolution layer, and at the end is the layer that is with the neurons, right?
Right.
In any network.
Yeah.
So one is a convolution and other is a fully connected layer. So in UNet, we are not using fully connected layer, right? Then if we are not using fully connected layer, then how is the probability getting calculated? Because if you know, in fully connected layer, we can use softmax and other cross entropy functions, and we can, put it in the last layer and do the classification. But here we are not doing classification. So my question to you is, can we do classification with only convolutional layers?
So yes, so this is still a classification because the you're classifying each individual pixel as opposed to the entire image.
Right.
So each for a 3x3 convolutional kernel, you have for one single kernel. So suppose it's 3x3x1, you would have 9 neurons in the kernel, and you would slide that kernel over the entire image. And so from there you could train the weights in that kernel, and then to actually optimize that network and to compute the loss, you will also use cross entropy functions too, but that cross entropy function would be operated over the image instead of a flattened version of that image.
Yeah. So in general, if you refer to any papers, they use the term neurons when there is more flattened input. They are not using the term neuron when you do, convolutions. It's a very general term that you find on internet. So that's where the confusion is. So if you go to your slide where you compared the difference between mask-R CNN and UNet. Yes. Here as well, I think you made the similar argument. You said that YOLO V7 is more complex because it uses a fully connected layer, right?
Right.
However, YOLO V7 is also fully convolutional. Like YOLO V1 used fully connected layer. After YOLO V1, they removed it. And that was the biggest challenge that came, that if you remove fully connected layer, that means you're passing the flattening image through the neurons, not the other way. So you would make your model simpler. So here you made this argument, YOLO V7 uses fully connected layer, but after YOLO V1, there is no such use. They removed it.
Right.
Other than that, I have one more question. Now, what is the role of skip connections in your model? Exact role. Yeah.
Yeah. So skip connections, they bypass these deeper layers directly. So it actually retains more information of the original image.
Right.
And therefore it gives a broader view of that image, so that they're basically different levels of feature extraction in the network.
Right. So basically, if we summarize that, like you have skip connections. So what happens is, as you are decoding your image, you are losing a lot of your information, especially from the boundaries. And also because it is becoming now into, you say here, you have gone from a bigger image, say 248 into 248 to 16 by 16 pixel image. So you have lost all the boundary information. Now your image is very low resolution image. And now when you add skip connections, you are directly adding, are you doing concatenation, or are you just adding when you add the output of skip connections with the input of the image? What are you doing?
I think it's a concatenation.
Right.
I want to say it's a concatenation, but I think that's one way that could be done, but
Okay. Another thing is, you talked about the difference between binary cross entropy and categorical class entropy.
right.
So in the categorical class entropy, you added some kind of weights to your you can say in because here you have a positive pixels as your positive class, and your negative class, which is your background, is higher in number. So have you tried this in practice? Because the paper that I published, the categorical cross entropy in the UNet, it did not provide any great result. In fact, what happened is that it marked it provided more masks to my bubbles, because what it is doing, it is providing a bias towards all the negative class and against the negative class, and it's supporting the positive class. So when it's supporting the positive class, so it is marking more positive pixels. So, and it provided a huge problem with my code when I tried to compare that. So this is just an additional point, like for all imbalanced data, maybe it looks very attractive from the literature, categorical cross entropy, but when you really apply it, you would see that it makes more bubble prediction, and it predicts more what you call false positive.
Yeah, so simply because of the binary nature of background versus bubbles, so I think when I did it, I was looking at binary cross entropy. I was also looking at focal loss, which is a modification of the cross entropy function. And like on theory, it's supposed to support class imbalance better, but it didn't perform as well. So so perhaps it's because of the much smaller data set compared to, I guess, when they do self-driving or that kind of data. So yeah, I think binary cross entropy is just in general recommended.
Can, in your images that you have trained, can you point out what is false negative in your image? Do you have any example where you can point it to me where is false negative?
So this is a false negative.
Where is that?
So let me get a pointer. So this bubble here, it's marked by manual labeling, but it's completely missed by the CNN. So the pink ones are where the CNN and the manual labeling they both agree, and the red ones are marked by manual labeling but are missed by the CNN. And on the other hand, so I think there's a pretty good accordance between CNN and manual labeling. But for example, this bubble here, now I don't know if it's a bubble or not because it's not marked by hand, it's not labeled by hand, but the CNN identifies it as a bubble. So this could be a false positive, or yeah.
So can you comment something on the precision and recall? Because, precision depends on, true positive divided by true positive plus false positive. Recall is your true positive divided by your true positive plus false negative. So
Right.
what do you understand by these two terms? And in your code, what were the precision and recall values?
So I there's an F1 score here, but I actually removed it because I personally thought the intersection over union is the best measure for semantic segmentation procedures, so I didn't include that. But so I think I guess when it comes to precision and recall, the it it should they should be pretty they should have pretty similar values, just because there's actually not a whole lot of false positives or false negatives. So so I think they should have similar values, and there isn't a high imbalance between false positives and false negatives.
To me, those values are very important. For despite IOU is a good measure and you're getting 0.8%, because there are two things. Once you do UNAT, you can either compare directly your black pixel with your black pixel in the ground truth, a
Right.
white pixel with the white pixel that you provided during masking in the ground in your ground truth. This is one way to do it. However, other advanced paper, they are comparing an object wise. So what they do is, whatever masks that you provided in terms of white pixels, they are taking it as one object. And then they are comparing it. So that is known as object wise comparison,
Right.
So that's one thing. And could you comment on the boundary? Like in for helium bubbles and for everything, we need to have a very good boundary information, because the shapes are extremely important for radiation effects
Right.
user case. So what can we do to improve the shapes? Because I see your predictions, however, they are small right now. If you zoom it, right now you have just marked with dots, but if I replace the data set with voids, the kind of data sets that we have, discussed, those polygonal data shapes,
Right.
then what is the what's your remark on that? How do we improve it?
Right. So the first step would be to actually label them properly. So when for this data set, because we assume the bubbles are spherical, so we just use the circle 2 on image J. Some of them might not actually be as spherical. So labeling the data properly is the first step, and then to actually better extract that boundary, that would come from the post-processing step. So I think it would be highly dependent on what sort of algorithms you would use to actually extract the labels that are predicted, because the CNN just throws the label out. It does not discern their shapes or anything. So I think the post-processing step would be important in selecting the right algorithms for actually measuring your features or extracting your features from the mask.
Right. So there is something known as, I think that's just a last remark before we conclude your presentation. So you need to have you heard about something called distance loss functions?
I guess I'm not familiar with that.
Yeah, distance loss function, it actually it's kind of loss functions which are based on for an object, if you define the center and that from center you are defining the boundary. And that kind of loss function, it really optimizes the boundaries of your objects. So
Right.
I would share a paper with you after this. But nice presentation. Thank you. So we move to Jacob now.
Thank you. Okay.
Thanks, Tommy.